Hello. So this first short lecture basically just presents an introduction to sequence stratigraphy. And there's some pre-reading here, which I hope you've already read, to sort of set the scene of what we'll be covering here, and actually in some of the following lectures as well. So what is sequence stratigraphy? Well, it's a tool or really an approach, a set of concepts which allows us to interpret time relationships from our observations of sedimentary rocks. And why do we want to work out time relationships? Well, it helps us to correlate between different sedimentary sections and also to map out in between those sedimentary sections, which allows us to predict. So predict the distribution of reservoir, source, seal lithologies. Um, and it also provides us with a model to guide interpretations in areas where we don't have much data. So what are the kind of benefits of this kind of analysis? Well, firstly, it provides a way of thinking which allows us to integrate data from many different sources. So that includes seismic reflection data, wireline logs, cores, biostratigraphic data, production data if we're thinking about reservoir scale, and also information from outcrop analogues and other analogues, systems that we consider to be similar in important ways to the ones that we're trying to understand. It also allows us, or it sort of forces us to think about time and how we relate time to a rock succession. And typically we do that by interpreting a hierarchy of different stratigraphic units. So the big scale sequence, and then within there, systems tracts, parasequences, and smaller scale features. And we also think about the surfaces that bound those different stratigraphic units. So this slide, the detail isn't important, but just to say that, you know, there's a long history of trying to interpret time within sedimentary rock successions. That predates 1949, which is the oldest reference shown in here. But really what we think of as sequence stratigraphy today was sparked by the advent of large volumes of seismic reflection data in the late 70s. And then there was a series of attempts to try to relate those seismic data to rock data from well logs and cores and outcrops, really through the 80s and the 90s. Different approaches to doing that. We're going to be using the nomenclature, the terms that were used really by Exxon, who pioneered a lot of this work in the late 80s and early 90s. So I showed you quite a complicated diagram on the last slide just to say that this subject, sequence stratigraphy, has quite a complicated historical development. And one thing that means is that there's a lot of different terminology, which doesn't always make life simple in terms of trying to understand the concepts. What I would say is that almost everyone of those previous schemes, they use the same method. So what that means is the tool of sequence stratigraphy is quite robust in how we apply it. But those different schools, they tend to emphasize different surfaces, different stratal packages as being important. You know, well, some schools emphasize one type of surface, other schools emphasize a different type of surface. And I'm afraid there's lots of nomenclature and jargon. I'm going to try to keep the language simple, but if I do use terms you don't understand, then please ask. I think the other point to make early on is I've already sort of tried to make this point that the method of applying sequence stratigraphy is different than some of the models, conceptual models, which go with sequence stratigraphy. And I think the key point about models is that you know, they're simplistic, they're simplifications. And probably a model that many of you are now getting used to would be a tube map of central London compared to the reality of a geographical map of central London. You look at the tube map and you can see the arrangement of the tube stations. You can see the underground train lines that link some of those together. And this is quite stylized. You know, distance isn't represented very clearly on this this tube map, but on the other hand, it captures important elements about how the tube stations are positioned spatially with respect to each other. So even though it's somewhat simplistic, it's useful. And this is true for, you know, other conceptual models that we use all the time as well. We know that the detail may be incorrect, but what we're trying to capture are the generalities within these models. So there are two basic concepts that are important in sequence stratigraphy, and you know we can explain stratigraphic patterns that we see and that we interpret in terms of these two variables. So the first one is accommodation space. That's the space that we have available to fill with sediment. Okay. The second key parameter is sediment supply. So that's basically the sediment we have available to infill that space. And it's the balance between accommodation space and sediment supply, the balance between those two things which is important in determining patterns in stratigraphy. So remember those two important controls, accommodation space and sediment supply. We're going to try to relate observed patterns back to those two. Accommodation space, okay, so the space we have available for sediment to accumulate, that again requires a little bit of thinking. So, you know, if you think about this, the top, we can think about a volume we're going to fill or have available to fill with sediment. The bottom part of that volume is essentially the basin floor, the sea floor. The top part, well, that could be sea level if we're thinking about shallow marine successions. If we're in a lake, it could be lake level. But if we're thinking about strata deposit in very deep water, then maybe we need to think about having a different surface to which deep water sediments will build up to. Equally, if we're thinking about rivers, for example, or continental rocks, then that they won't build up to sea level. They will build up, for example, to an idealized stream profile. Now we'll come back to that. We'll talk through fluvial, river deposited rocks and deep water rocks later on. But just to say that sea level is not a good sort of mental picture of how much space we have to fill up to in those rocks. Okay, so we're going to start off keeping things relatively simple and think about shallow marine settings. And these three images here are three cross sections. On the left, we're at the landward side or near the basin margin. As we move towards the right, we're moving towards the center of the basin into progressively deeper water. And what you can see in each of these three diagrams, we start off with an idealized profile. So this could be the shelf or the coastal plain. Then basically we have a slope. This could be a continental slope and then a deep basin. So the idea is this geometry sort of mimics what we might expect to see at a passive continental margin. And then within there, we can basically see how sediment is built up through time. So we have 1, 2, 3, 4 packages of sediment with these lines in between them representing timelines within the section. And in this diagram here, we're assuming that sea level starts off here and sea level rises during deposition of those 4 units. And you'll see all three of these diagrams have the same starting point. They have the same geometry: a shelf, slope, basin floor, shelf, slope, basin floor. And we start with sea level in a relatively low position, and then sea level is rising in relative terms to a final position. So what's different between those three diagrams? Well, Accommodation space is the same. Accommodation space, in this case, reflecting how sea level changes. That's the same in those three diagrams. What's different is sediment supply. In this top diagram, we have a low sediment supply, and what happens is if we look at the facies boundaries, these zigzag lines separated by different types of shading, they move towards the left, they move landward. That's because sediment supply is not keeping pace with the rate at which accommodation is being added. So the facies belts are stepping back towards the basin margin, and that would be transgression or drowning in shallow marine rocks. The middle diagram here, we have high sediment supply. So if you look at these facies boundaries, they're building out, they're moving out towards the right. They're also moving upwards as well. They're keeping pace with the rate at which sea level is rising, moving to the right. So sediment supply is outpacing. It's faster than the relative sea level rise. And therefore we have the system building out. That's regression or progradation. Two terms mean the same thing. And then we can have this situation at the bottom where, again, relative sea level is rising, but if we look at the facies belts, they're basically staying in the same position. So in this case here, what we're seeing is that sediment supply is basically keeping pace with accommodation space or relative sea level rise, and the facies belts are just building up vertically. So sediment supply is important as well as accommodation space. Okay, by systems tracts, what do we mean? Well, a systems tract is really, it's a linkage of contemporaneous depositional systems. What that means is a series of systems, depositional systems, which are linked to get together at the same time. So if we go back to this diagram in here, non-marine coastal deposits, those could be river systems, for example. They pass towards the right into littoral deposits. That's shallow marine deposits. And then as we pass towards the right even further, we're into effectively muddy offshore marine deposits. So these three different types of shading, the implications, they're all forming at the same time, they link together, and that would then satisfy our definition of a systems tract. Now, systems tract can also mean these are occurring under specific sets of conditions related to accommodation space and sediment supply. And the models I'll talk through a little bit later, they occur, those conditions occur and they're linked to specific parts of a relative sea level curve. Once we start to link those packages of strata to different parts of a sea level curve, we also say something about, well, what type of surface overlies them, what type of surface underlies them. So we can also say something about the surfaces that bound them. Internally, well, the fact that these systems tracts represent a certain combination of accommodation space and sediment supply, so internally they have a distinctive parasequence stacking pattern. They have a distinctive architecture that records either progradation or aggradation or transgression. And as I said, in the models I'm going to talk through, they occur in a certain kind of order that represents a sea level cycle. Okay, so before I show you those models, I'm going to show you two sets of models, one at the top and one at the bottom of the screen. The one at the top is for a shelf break margin, so that's a, if you like, is approximating a passive continental margin with a shelf, a slope, and a deep basin floor. So clear breaks in angle between those different segments of the basin margin morphology, basin margin shape. Distinct angles associated with those. Obviously, where we have a change from the shelf to the slope, there's also, you know, an abrupt increase in the deepening of the water depth. So these basins have the potential to have deep water deposits. And as I'll show you later on, you know, falling sea level is marked by an unconformity with specific characteristics in a basin with a shelf break margin. Okay, you'll also see models at the bottom of the screen that represent the same accommodation, well, the same sea level and sediment supply conditions, but in a basin with a different geometry, one that has a uniform, gentle dip from the margin towards the center. So a ramp type margin. So yeah, uniform low angle dips. There's no abrupt changes in water depth. The water depth gradually increases as we go from the margins of the basin towards the center. And in this basin, falling sea level has a different expression to what it has in a basin with a shelf break morphology. Okay, so here are the first two models. The model at the top, this is our basin with a shelf, shelf in here, a slope, a basin floor. That's the top block diagram, and I'll show you similar block diagrams on the following slide. They'll all be at the top. Basin with a ramp margin, you can see just a very gradual increase in water depth towards the right. At the top here, we have a relative sea level curve, and this is shown as basically it's a sinusoidal curve, sea level going up and then down and up again, defining this sort of sinusoidal geometry. But we're also assuming the basin is undergoing subsidence, and that means that this up and down motion is superimposed on an overall upward increase in accommodation space. So this assumes that we have tectonic subsidence of the basin, which is relatively uniform through time. So yeah, so high sea level, high relative sea level, the curve is going up. Falling relative sea level, the curve drops down, and then time starts here and moves towards the right. Okay. So for this part of the curve where sea level is rising, but it's rising and starting to, the rate of rise is slowing down, so it's reaching this sort of highest point in here. Well, in these models, we're assuming sediment supply is uniform. And in that case, you know, the high rate of relative sea level rise, or we have this vertical stacking, and that vertical stacking or aggradation then switches to a combination of vertical plus also basinward stacking. So this would be progradation or regression. So this is a kind of stacking pattern we expect to see that reflects this increasing accommodation, but the rate of accommodation getting slower through time. And we see the same pattern in a basin with a ramp margin, upward building or aggradation, and then that gradually changing into a combination of upward stacking and also basinward stacking, so regression. And in terms of different parts of the sea level curve, we refer to this as the Highstand systems tract. Okay. So let's move now to carry on through the sea level curve. We've reached the highest point, and now sea level is falling. Okay. So we're looking now at a part of the sea level curve which is linked to the falling stage systems tract. Sometimes you might see this referred to as the early Lowstand systems tract. The key thing though is we're thinking about relative sea level and the accommodation changes that imposes. We have a decrease in accommodation. So if we look now at this top diagram, remember this is our basin with a shelf, slope, basin floor morphology. We see the shallow marine rocks in yellow, they're downstepping. We see rivers cutting valleys, they're cutting into the older Highstand deposits. They're also cutting down into these falling stage shallow marine deposits. And those valleys are actually extending as far as the shelf edge in here. And once those valleys are cut into the shelf edge, well, any sediment that's supplied through that valley, the sediment that's being eroded and reworked at the base of the valley and at the sides of the valley, that's all going to move further downstream. So it will reach the shelf edge and then it will be bypassed through canyons on the slope, and it will be deposited on the basin floor as submarine fans. Okay. So the key thing here is this falling stage, this lowering of relative sea level is expressed as valleys, so deep fluvial erosion on the shelf, sediment bypass through canyons and sediment predominantly accumulating on the basin floor. If we look at this bottom diagram, so this is again our basin with a ramp morphology, we see that basically the shoreline is deposited as a series of sort of downstepping units. Okay, that downstepping is recording the fact that relative sea level is falling, and because we're still adding sediment to this, the shoreline is being pulled further and further into the basin. It's basically following the position of relative sea level as relative sea level falls. So what do we see in here? Well, again, we see rivers cutting valleys. We see the shoreline moving a long way into the basin, potentially also accumulating quite thin units which have a very large extent from up dip landward to down dip basinward, with valleys cut into the top of them. Okay, so now we're thinking about sea level starting to rise in this purple part of the relative sea level curve, but starting to rise slowly. And this we would refer to as a Lowstand systems tracts, or in some models this might be referred to as the late part of the Lowstand systems tract. The key thing is, in terms of this relative sea level curve, relative sea level is now starting to rise, but rise slowly. So if we look at the top diagram, again, this is our basin with the shelf, slope, basin floor morphology. Well, the valleys are still acting to feed fluvial sediment in towards the basin, but because relative sea level is rising, we have some space now at the shelf edge to store some of that sediment. So we might accumulate shallow marine sediments in orange in here. And we also start to accumulate deeper water sediments on the slope itself. So this brown unit in here, for example, would be a deep water fan, but one which is confined to the slope. We've essentially abandoned those fans on the basin floor. Okay. If we look at a basin with a ramp margin, well, now again we're starting to produce accommodation space that we can fill in a relatively position which is relatively close to the basin center, and we start to accumulate shallow marine and coastal plain deposits near the basin center. Okay, but we still have valleys present towards the margins. At the margins here, effectively we have no accommodation space. We're still bypassing sediment towards the basin center where we have a accommodation space. Okay, so now we move further on. Sea level is rising and rising fast, and we're now thinking about part of the sea level curve that corresponds to the transgressive systems tract. So in this case here, because sea level is rising fast, the rate is that it's fastest, then basically we're able to outpace sediment supply. And what that means is the shoreline is stepping from basinward to landward. So we have transgression. So what does that mean? Well, we basically start to flood and drown these valleys, and those valleys can be their mouths can have this sort of funnel shape, which is where an estuary might develop. So that's basically a drowned fluvial valley with some marine influence in the form of waves and tides. We've abandoned shallow marine deposits at the shelf edge and also deep water deposits. We basically have no non-deposition at the shelf edge and further into the basin, and instead the shoreline backsteps towards the basin margin. Okay. We see something similar in a basin with a ramp margin. So again, we've abandoned these shallow marine and coastal plain deposits near the center of the basin, and basically the shoreline is stepping a long way back towards the basin margin. We're also flooding and drowning incised valleys on the shelf here. So transgressive systems tract characterized by backstepping of the shoreline. It's moving towards the basin margin, drowning of valleys, and non-deposition. So, effectively we switch off sediment supply to the basin center. I should say that, the next part of the sea level curve, we're back to where we started in this series of diagrams. So if I go back to here, the final part of the sea level curve is a repetition of this Highstand systems tract, the system building out and building to the right again. Okay. So I've just shown you 4 series of diagrams that talk you through 4 different parts of a relative sea level curve. Those 4 different parts of the curve with different conditions of accommodation space and sediment supply, and we refer to those as 4 different systems tracts within these models. Again, bear in mind these are models, they are simplifications, but they capture some general aspects which are useful when we come to interpret. Okay, so here is a cross section from landward to seaward. This is for a basin really corresponding to the top of the upper series of these block diagrams. We take a cross section through here. The colors are slightly different because these are taken from a different publication. So the colors in here, green is coastal plain, yellow is shallow marine shoreline, essentially. Grey, various shades of grey are mudstones, offshore mudstones. Reds or oranges in here are, fluvial or estuarine deposits, so really valley fills. And then the browns in here are deep water deposits. So we can see, a Highstand systems tract with basically a aggradational to progradational stacking of shallow marine deposits. The red line in here is the unconformity. That's the deep erosion surface cut at the base of rivers as they cut down and cut valleys. And that red surface, we can basically correlate that onto the basin floor. And as we have erosion on the shelf, we have bypass of sediment, sandy sediment onto the basin floor to form deep water fans. We then, and in these models, the falling stage systems tract and the Lowstand systems tract in the 2 previous diagrams are sort of grouped together. Then above that, in green, these dark green deposits are condensed deposits. So though effectively they form when we shut off sediment supply to these sort of outer shelf, slope, basin floor regions. And those are accumulating when the shoreline is backstepping, when it's retreating. So this would be the transgressive systems tract in here. Okay. The point at which, the furthest landward position of the shoreline, that's often referred to as the maximum flooding surface. That's the point at which the shallow marine deposits are pushed furthest back towards the basin margin. So that's an important surface within these models. And then above that, the shoreline builds up and it builds out again. So this is back into the Highstand systems tract. This is a similar model, but for that ramp margin, similar cross section. So again, going back to these block diagrams, taking this cross section in here, coloring it slightly differently. So again, green is coastal plain, yellow is shallow marine, grey is offshore mudstones, and red in here are valley fills. The Highstand systems tract characterized by aggradation and progradation, this vertical to basinward change in the shoreline position. Red in here being the line which is marked by the formation of valleys, and also this big sort of shift towards the basin center of the shoreline. The transgressive systems tract recording the retreat of that shoreline, and then the maximum flooding surface in here, that again is defined by the most landward position of the shallow marine rocks in here before we build out again in our second Highstand systems tract. Now, one key thing in here in these models, you see, particularly if you look at the shallow marine rocks, you'll see that the shoreline has this kind of high frequency sort of zigzag pattern associated with it. That's also present in the block diagrams. If you look at these we have a number of sort of lines in here which are really timelines through here, and they bound smaller scale packages within what we were describing as systems tracts. So those smaller scale units are parasequences. We'll say a lot more about those tomorrow when we look at shallow marine rocks, but you can think about these as being the building blocks of these larger scale systems tracts and sequences. Internally, you know, they're relatively conformable. So what that means is internally those parasequences don't have surfaces that record big breaks in time, for example. Internally, they're made of shallowing upward successions, and these are typical at a scale that we can recognize in cores, wireline logs, and outcrops. So they lend themselves to being visible in some kinds of data. The larger scale patterns, as in this model, or this one, here we're looking at large scale stacking of different units, and that really lends itself to seismic reflection data. So parasequences are important units that record shallowing upward, and they're bounded by units that record flooding. So abrupt increases in water depth that correspond to pushing the shoreline slightly further landward. Okay, that's represented here by this sort of backstepping, these small backsteps in that red to grey fascist boundary. So internally, those parasequences, again, we'll say more about this tomorrow, but they tend to record relatively deep water deposits, shallowing upwards into shallow water deposits. And then at the top of those parasequences, we see a change back into deeper water. So in this case, a change from sandstone in shallow water conditions to mudstone above in deeper water conditions. Those parasequences, we've already kind of talked through the different models already, that we expect to see patterns of progradation or regression. We expect to see patterns of retrogradation or overall transgression, and then patterns where we see just vertically building up. Where the parasequences are stacked in a way that's progradational, that means we have sediment supply is outpacing accommodation space. And we might expect to see those in the falling stage, Lowstand and Highstand systems tracts. Where the parasequences are retrogradational, in other words, they're stepping in a landward direction, well, that means then that the accommodation space is slower. It's being outpaced by accommodation space. Therefore, we're having overall transgression, and these will be in the transgressive systems tracts. Where these parasequences or different units stack up vertically without any real change in water depth, then sediment supply and accommodation space are in balance. That's quite an unusual setting to have. So just to show that those sort of schematically, so this top diagram here, this is a progradational parasequence set. So again, this is a cross section going from landward on the right to seaward or basinward on, landward on the left, seaward or basinward on the right. And you'll see these parasequences are stepping towards the right, as well as building up vertically. So this is progradation or regression. The middle diagram, you see again landward on the left, basinward on the right, and you see the parasequences are stepping back towards the left. So in this case, that's retrogradation or transgression. And in this case, a sediment supply is being outpaced by accommodation space. This bottom diagram, the parasequences are just stacked vertically. They're not overall moving to the right or to the left, they're just sort of stacked vertically, and that's aggradation. So sediment supply basically in balance with accommodation space. What we can see if we take a vertical section through here is that, you know, in a progradational parasequence set or progradationally stacked series of parasequences, the lowest parasequence at any one point tends to record the deepest water deposits, and as we go upwards, we tend to see progressively shallower water deposits. In a in a series of stacked parasequences that record retrogradation or overall transgression, we see the opposite. The parasequence at the bottom records the shallowest water conditions, and as we move upwards, we see progressively deeper water deposits within each parasequence. If we look at aggradation, then each parasequence looks the same. So this is what we see in this bottom diagram here, that internally the fasces present within each parasequence, they're basically the same. They're in the same proportions as you go upwards through each successive parasequence. Just to give you some examples of what these look like. So here's a cliff face that's about 500 meters in height. This is composed of offshore mudstones, so relatively deep water at the bottom. The sandstone layers in here are shallow marine sandstones, so yellow in the cartoons I've been showing you. In this case, you can see as we go upwards, we see that each of these various sandstone benches in here gets thicker. You see what gets sandier upwards. And at the top here, we're into basically a coal-bearing coastal plain deposit, which would be green on those previous diagrams. So this is recording an overall progradation. This diagram in here shows something similar, or similar in terms of scale, about 200 meters vertical cliff face in here. We have a muddy section at the bottom, but including coals. So this is a coastal plain. This would be green colored in the previous diagrams. And as we pass upwards, we see interbedded shallow marine sandstones, which would be yellow in those cartoons, interbedded with coal-bearing coastal plain in green, yellow shallow marine sandstone. And then as you pass towards the top, you see those sandstones are getting progressively thinner upwards. So this would be a case of a retrogradation or overall transgressive stacking of parasequences. So again, just to go back, this diagram in here corresponds to this example. This middle diagram here corresponds to this second example. Okay, and why is this important? Well, so this top diagram is showing a progradational series of parasequences stepping upwards and also stepping out towards the basin center, towards the right. And if we have, maybe we need some biostratigraphic data to help support this interpretation, but in this case, this is showing 4 different parasequences, each stepping into the basin with some coastal plain deposits building out behind them. So this would be an interpretation, a correlation between these different wells that is honoring sequence stratigraphy. It's the different correlation lines in here are essentially timelines, and as we go from left to right, we go from coastal plain to shallow marine to deeper marine. So that's a consistent change from basin margin to basin center, and it makes geological sense. The bottom diagram, we have the same well data. In this case, we're basically doing a lithostratigraphic correlation. We're just taking the thickest sand and we're correlating that between the different wells. This correlation, well, this basically predicts one big continuous sheet of sand, coastal plain above, and then we have these rather sort of unusual shallow marine sands which are sort of stuck, enclosed within deep marine shales or relatively deep marine shales. So this doesn't make geological sense. You know, if we go from, you know, shelf-formed mudstone, so relatively deep water, into shallow marine and then back out into shelf-formed mudstone again, that doesn't give us a consistent sense of moving from the basin margin to the basin center. So this doesn't make sense geologically. Okay, so I think that's a good place for me to pause there. We'll now rejoin the main meeting. I'm happy to answer questions before we move on to an exercise.